My name is Jyrki Latokartano. I work in a coordination team of Trinity at Tampere University. Our coordinator, Professor Minna Lantz, was not able to join today. I will be presenting briefly the Trinity in the beginning, and then we can start going through the actual topics of the day, which are the industrial or company demonstrations. Okay, so Trinity is a Horizon 2020 funded project where our main goal is to improve the agility and innovation capability of European SMEs through robotics and IoT. And as all the digital innovation hubs, one of our goals is to build a digital innovation hub and a network that also exists after the Trinity project that will support the SMEs on these very topics, and they have a one-stop shop for companies to find information also after our project. Trinity Consortium has 16 partners from 10 countries, so we present Europe fairly well. We have altogether 9 research institutes and then companies and other organizations that support in our Trinity goals. And we have 3 thematic areas where we focus on Trinity. Those are robotics, IoT technologies, and cybersecurity. So basically, all the activities are on these domains, and our focus is on agile manufacturing. There are other sister projects on robotics that work on maintenance and infrastructure, agri-food, and so on. But Trinity DIH together with DIH Squared is focusing on agile manufacturing. Our concept is quite pragmatic. So the idea of Trinity is to showcase existing research results from different European projects, and those are so-called use cases that the core consortium of Trinity has presented 18 of them. And these use case demonstrations consist of different modules that we are polishing and making more easy to accept for the SMEs during the Trinity project. And these work what we do, and also examples and inspiration for the companies who are taking part in our open calls, which start so-called demonstration program. And the idea is that we create these modules that would be available for all the interested SMEs, and then you can pick the best of these modules for your own applications and then try to improve the agility of your robotics in your manufacturing company. We are now in the demonstration program 1, which started this summer, and it will last for 12 months. And today, all the talks what we hear are from the consortiums of our demonstration program 1. It was quite popular. We had 115 applications from 27 European countries or related countries in the Horizon 2020. So altogether, nearly 300 companies applied for the funding. So it was quite a work for the open call evaluators, technical and business experts, out of which we selected the group who evaluated the proposals for the open call 1. And then finally, after the checks and selecting these applications, we funded 19 proposals that cover 44 beneficiaries from 14 European countries, which you see on the map on this slide. And the total requested budget of these demonstrations was 4.66 million euros. Started in July, as mentioned, and they will last from 9 to 12 months. So we've been now going through, we have a first quarter of the demonstration program is now completed. From Trinity point of view, each of these companies that and the consortiums that you will hear the presentations in this series of these webinars, they have been assigned a mentor from Trinity Consortium, and this has been quite successful, at least from the Trinity point of view. We have now a much closer contact to the companies that are doing the demonstrations for us, and hopefully we can also, as the consortium, support them better, because we have some companies who have never received EU funding before or have not necessarily done much R&D activities in their work, so they can get different support for these mentors and hopefully succeed better than in their own goals and in their future businesses and activities. Before we start going into these demonstrations, a quick mention about Trinity's second open call. So during the Trinity 4 years of running, we will have 2 open calls, and the timeline for the second open call will be published in November. It's similar as the first call, but this time the maximum funding is slightly smaller, and we hope the demonstrations to be slightly shorter. Total budget for this second open call is 3.5 million euros, and we try to enhance the European dimension even more, so we are looking for multinational consortiums in our second open call. But that was all from my point of view as a background for the Trinity and Trinity demonstration program, and now we can move to the actual topic, where in our first webinar the topic is focusing on additive manufacturing technology and related technologies, and then we have 3 other webinars coming, and this duration is 90 minutes, and the idea here is that we have 1 presentation from the Trinity Consortium first in this webinar, and then we have 4 demonstrators presenting their work, and each presenter has 5 minutes for pitching his or her topic, and during that you can write questions in the chat window, which we can then answer in a 10 minutes of discussion we have after each presentation. Of course, you can also raise your hand after the pitching is over and then ask your questions then, and I hope we have a very active and fruitful conversation after the presentations. The program for today is listed on this one. The times are fairly indicative, but without further talk, I would once more like to welcome you all for this webinar. I hope you enjoy the content and we have a good discussion. Our first presenter will be Haldor Arnarsson from the UIT Arctic University of Norway, and he's going to give a presentation on wire arc additive manufacturing with industrial robots. Okay, Haldor, the floor, or more likely the screen, is yours.
Thank you for the introduction. Will now share my screen. Okay, yeah, so my name is Haldor. I'm working for the Arctic University of Norway as a research assistant, and I am a developer for the Trinity project. I will talk a little bit about metal 3D printing, then I will talk about our internal use case. So robotic welding and additive manufacturing. So 3D printing is becoming more and more used in today's industry. However, it can be extremely expensive to invest in a large metal 3D printer. One example we have from UIT is that we have bought a hybrid 3D metal printer, which is able to print quite large parts with metal powder. However, the machine is extremely expensive, and also the powder is very expensive. Another method might be to use automatic robotic welding. So you combine this with wire arc additive manufacturing, or WAM, to 3D print parts by using arc welding process to create 3D metal parts. The benefit of using a robot arm is that you can print parts that can be as large as the robot itself, which again increases the flexibility, and you can also use it to repair parts. And also it can be very often very inexpensive to buy a second-hand robot and a welding torch, and then you can have potentially a 3D printer or a metal 3D printer. So here at UAT, we are developing use case 5, which is a internal TRINITY use case, which is wire arc additive manufacturing with industrial robots. So the setup of our system is that we have a KUKA robot, and then we have a rotary table. This enables us to do more advanced welds. We also have a TIG welder. What is special about the TIG welder is that the robot usually has to move in the direction the wire is fed. And therefore, having the rotary table, it enables us to do, again, more advanced welds. These three components, the KUKA robot, rotary table, and TIG welder, they are connected to our KUKA controller. This is then part of our physical system. We have then created a digital twin of our system, a digital counterpart, in Visual Component, which is a simulation software where we have created a replica of exactly our robot cell. However, to be able to connect our physical part and the digital part, we are using the OPC UA server. This is just an information server for sharing information both from the robot to the simulation software, but also from the simulation software and to the physical robot. So this system. So using the simulation software and Visual Component, it allows us to use the functionality which is in Visual Component, which is it has a rather intuitive and simple programming method with drag and drop function, but it is also able to automatically generate paths. So if you have a CAD model and you have a path you wanted to move, you can press on the curve and it will automatically generate this path. You can also use the system to remotely monitor the robot while it is moving and welding. And again, we get all the functionality from Visual Component. So Visual Component has also been starting to add VR functionality. This again, we can add to our system to create an even simpler method of programming the welds. And the system is made to be one-to-one, which means just that 1 meter in the simulation software is 1 meter in the physical one. And here I have a short video showing welding two metal plates together. So here we're running a simulation. This is to validate and reassure that the program we have created is right, there's no collisions, and it looks okay. And then afterwards, we can directly run this program, which we have created in Visual Component, straight on the physical robot without almost any intervention, which decreases the time it takes to program and set up such a system. I also have a second video showing using the path function. As I mentioned before, we can press on a curve and you automatically get the path the robot will move. And this is to show filling up the gap by using welding, for instance, for repairing parts. And then afterwards, when you have programmed it, you can run it straight away on the physical robot. This time it's without the welding on, because you can't see too much of the movement, well, because the light is so bright. So additive manufacturing, this system is also capable of creating structures. In visual components, we can create and 3D print simple straight lines, which we have done before. Our old program only allowed for straight lines, but since we have visual component now, curves. However, one problem we are having is that the process of doing this arc TIG welding, it's very time consuming because of all the heat. So one of our goal and what we're going to continue on improving is to increase the automation of the system to create it more automated, but also be able to create parts faster and also more complex and bigger parts than you can see here on the pictures. So the benefits of our system. Yeah, as I mentioned before, one of the benefits is easy planning and also having the ability to do offline testing. With our system, you can be somewhere else in the world practically as long as you have a visual component. You can configure and make a new welding program and send it directly to the robot cell, which increases the flexibility quite a lot. Also, the method. So the method, how we have created the program, we have made a unified method for the robot program. So this means essentially we can switch out the KUKA robot and put in a new robot, and it will still, everything will still work as long as we have a visual components file of the robot in the library. So this again more increases kind of this software and how we're working. And also the 3D metal parts that we print, we can use for both rapid prototyping. We can also do reverse engineering, material testing, and also hybrid testing. And no, hybrid manufacturing, I mean, sorry. Yes, that is it for me. So there is a post processor in visual components, so I'm able to read all the points and all the XYZ coordinates of the program created in visual components, and then I take all of these data, also the speed. I have my own Python program which takes the data and kind of sort of sets it up and sorts it and then executes it on the robot. So I have kind of my own Python translator that takes all the stuff from visual component and puts it straight on the physical one.
Yeah, I have a quick question regarding the control. So basically I see there's a turntable, right? And which is moving according to, like, it's actually complementing the robot movements. My question is, how do you control that turntable and how is it synchronized with the robot?
Yeah, so here we come back to visual component. The great thing about visual component is that there is this drag and drop function, so you can just add the rotary table to the robot directly, then it's kind of a part of it. So then you just have to jog the table and then and the robot, and then they all move simultaneously, and then you can create kind of very advanced movements, but in a very simple manner using visual components. Yeah.
All right, thank you.
Well, good morning for those also who joined us during the first presentation. So my name is Jyrki Latokartano. I'm the project manager in Trinity, and I'm moderating this webinar. And we now move on to the first actual external demonstration. So demonstrations completed by our companies who are part of the demonstration program. And the first speaker is Robert, CEO of Additive Automations in UK. And they are focusing on a problem that especially powder bed based additive manufacturing technologies, they are a great method for creating parts and producing things that you cannot manufacture with any other technologies. But what is not that much discussed about when promoting AM technologies, there is a lot of pre-processing and even more post-processing of these components. And the Salsa 2D is focusing on these problems. So go ahead, Robert. Screen is yours.
Good morning, everybody. Yeah, I'm talking to you at the moment from the heart of Britain, up in the north of England, called Sheffield. Also known here as the Steel City, actually sitting on top of some infamous Orgreave mines, which changed the landscape of industry in this country about 35 years ago. And now it's one of the most concentrated advanced manufacturing parks in the UK. It's got some companies such as McLaren, Airbus, Boeing, Rolls-Royce, and it also includes our partner, who's also on the line, James Law, is representing the University of Sheffield, and we're working with them on this, and obviously with Trinity. So the problem that we're trying to solve in this project and the wider company is AM enables the digital manufacture of high complexity parts in multiple materials, but it's finishing those parts that is still largely manual process, and that can make it uneconomic for production volumes. So the mission is to A, eliminate the barriers to entry for using AM in volume production, B, complete AM's digital thread by automating those manual, dexterous and toxic steps, and C, to bring dexterity and reasoning to industrial robotic arms through AI, vision and sensing systems. So some of the benefits of the system will be, one, this source of defects is human error. So a 90% reduction in defects across post-processing. 2, robots can do repetitive, mundane, strenuous tasks for longer and more efficiently. So a 10x reduction in operational costs. And also the toxic powder, such as nickel, cobalt, chromium, and some of the nasty tasks that can cause RSI, basically eliminating that. So humans don't do those, and they do more of the creative, more of the creative tasks. So our USP is that the economics of logic-driven automation or traditional automation doesn't really stack up for additive for many reasons. So we're creating autonomous control systems. We're using vision and force sensing to do that. And we're creating a software application, one that would be integrated to do teach, simulate, and control, all from that one application. So the solution is a mixture of hardware and software, some bespoke tools that we design, a vision system or a couple of vision systems, one for local position correction and one for dynamic or global or absolute robot accuracy. And then the one there on the bottom right, which is what we're doing in the Trinity project with the University of Sheffield and the AMRC, is a digital twin. This whole notion of being able to import a CAD model and getting a robotic path out of it autonomously, which you would have to use some AI to be able to do that. So to really summarize the solution, it's all about building automation software that is specific to AM post-processing. And that kind of is about integrating the 3 core aspects of robotic automation, so relay control. A little bit of, here we go, skip the slide. You can view some more photos and videos on our website. But this is our cell in one of the factories of the University of Sheffield has. This just shows one of the end effectors and one of the parts that we're currently working, which is a satellite bracket for aerospace. So a bit of context as to why now. Because the events of the past year really have triggered a drive to digital manufacturing. So on the top, we'll have a timeline that are kind of triggers, and on the bottom left, we'll have drivers. So I think the first trigger was just Norsk and Boeing printing the world's first TI component and showing that it can be done in commercial safety critical applications. I think an important trigger is the fact that we need to look at local manufacturing to reduce supply chain risks, not just the UK leaving the EU. Whether we like that or not, it's a fact. There are other factors such as the US, and I'll get onto this with banning Huawei and other Chinese companies, and we do need to look at reshoring manufacturing. I think COVID-19 has again showed that reshoring manufacturing is important to again manage that supply chain risk, but also have a flexible production line. The UK ventilator challenge, Boeing printing thousands of face masks in dozens of locations across the US. Huawei, again, as I said, was banned in the US and in the UK, and is again another supply chain risk. So local manufacturing or reshoring of manufacturing. And for me, the most important, which is a net zero economy, additive manufacturing has huge capability here. It's got design freedom, it's got near net shape capability. So you've got opportunities for lightweighting, thermal efficiency optimizations, near one-to-one by-the-fly. And you can change the product life cycle to prioritize refurbish, repair, and recycle. So, and this one here is most important for me, is this climate emergency, and to try to solve that. But we won't be able to get to this prediction of over 46% of manufacturers supplying AM in low to medium volume production by 2023, unless we sort the economics out. And that means really reducing the current cost by a factor of 10. And that's going to be a combination of materials in AM, design, the actual additive process, but also automation. And that's what we're using robotics for, is to really bring that cost of post-processing down by a factor of 10. And that's us. And that's our vision, really. And in pursuit of a digital and sustainable future, we automate the additive manufacture of polymer, metal, and composite products. And be happy to answer any questions.
Thank you very much, Robert. Any questions? Either write to the chat or raise your hand, and I might ask one while people are still formulating their questions. From technological point of view, what do you think is sort of like the most challenging things to solve if we think about robotizing these processes?
Yeah, it's a really good question. I think the most tricky part here is control. And that's going to be partly solved with sensors. So we've got these 4 sensors and this vision system, 2 vision systems, and that's because we've got quite complex parts, and parts that change between builds, but also within builds. If you've used additive a lot, you'll know that not only does one build to another change in terms of tolerances, but also within the build, depending on where you build in that chamber. You can have quite different deformations and distortions, and while the parts still may conform, you need the robot to be able to adapt. And how do you do that without reteaching? Well, the answer is you can't. So you need to bring what a human does, so human capabilities like dexterity, reasoning, real-time feedback, to a robot. And the only way you can do that is with sensors. So we're trying to do a hybrid approach with position, local and global position, and force sensors. And that's going to be the most challenging aspect of this.
Sure is, yes. It involves a lot of sensors and calculations needed to be done. So it's not just a simple machine tending application for sure. There's quite a lot of things involved.
Yes, the post-processing, the depowdering, platform removal, support removal, witness removal, these tasks between the print and the machining. Not all parts need machining, so sometimes just inspection, but everything that happens between print and machining, or print and inspection, in between there, that's what we want to automate.
Tom is going to talk to us about laser cladding, also a very interesting project, but still quite a niche area, requiring quite a lot of specific expertise from the operators and the users, and also having a lot of very sensitive parameters and others, which, if not controlled correctly, may damage a quite expensive process and a workpiece. But on this problems, we heard the presentation. So go ahead, Tom.
Yes, hello, good morning. My name is Tom de Bruyne from Laser Cladding Ventures. And yeah, we are very happy to be part of the TRINITY Consortium. And our project is the LDM-AUTO project with the objective to automate laser cladding. Good. You can see my next slide. No, you can't see it like this. Yeah.
No.
So laser cladding. So our company, what we offer, we actually offer two things. We do R&D in 3D printing with the technology, but our main industrial activity is wear protection for critical assets. The example you see here is a petrochemical barrel of a compounding installation, and then typically you see that we would line it with, for example, Stellite 21, which is a cobalt chrome alloy, and in the laser cladded state, it features extra hardness, so it creates to better wear resistance. Yeah, the technology that we use is laser cladding. Yeah. And basically, what for us the focus is that we do not apply it for repair applications, but mostly for volume applications. That's our goal. Yeah. If you see it, the opportunities we have, then I think we have a strong USP. Yeah. In that hard-facing niche, but we also have challenges. Yeah, the USP is that with laser cladding, welding process where you apply laser power and you create a specific metallic structure, and a bit across the board, laser cladded coatings are up to 20% harder than conventionally welded or thermally sprayed coatings. Depends a bit on the material type, but yeah, in general you can expect extra hardness. Yeah, and what we also see both on lab testing as with it quite often we see that the extra hardness or the better metallic structure, it results in an improved wear resistance up to 4 times or even 8 times we saw already. Yeah, so it's a strong USP. Yeah, but on the other hand, there are still definitely problems and issues. Yeah? And to really apply this USP for volume applications, we need to improve the uptime of the machines. Yeah? So I think machines should, in a factory environment, have 80% uptime. Yeah, to combine productivity together with flexibility. Yeah, the yield loss should be below 1%, and ideally in pro mil. Yeah. And also the machines are actually not turnkey, so it's relatively difficult to have them activated 24/7. Yeah. So what we typically see is that our machines are operated by engineers, white collars, and only on specific tasks, blue collars can operate the machines. Yeah. Good. And so if you look then at the technology itself, yeah, it are actually two things. It's a welding process. Yeah, we use laser power. We project metallic granulate, powdered material, and we melt it on a substrate. And then you see this is a process how it looks, and we apply a wear-resistant layer. Yeah, and basically, if you have a good melt pool, yeah, if you control the quality of the melt pool, then you can control the quality of the clad. Yeah. Another thing is that's the downstream process. The upstream process is, basically we have a robot, and it controls the laser cladding head, and it's also typically a motion system for the substrate. We have a powder feeder, we have a laser. It's connected to a controller. And basically these are the elements of a laser cladding installation. And basically to control the quality, you need to control the upstream process, but you also need to control the downstream process. And then if we look at from our experience what the problems are, first of all, you have quite a lot of failure modes to do, also because we use high power laser between 1 kilowatt and 12 kilowatts. And then you can have upstream problems, for example, overheating of the clad heads. For example, problems with the feedstock, with the powder feeder, etc. But you also can have, for example, downstream influence of the substrate. You can have your welding process, which becomes unstable, etc. So you have quite a lot of failure modes that can affect the quality of the clad. Then the second thing is that, as we do it today, the process is that it's really operator driven. So it are the operators who load the machines, it are the operators who set up the machines, and it can be quite cumbersome. And the other thing is that it's also the operators who are basically checking every 5 minutes, every 10 minutes the process to see if the melt pool is stable, to check a number of sensors, etc. In the installation. But in reality, we still have quite a lot of machine downtime. We need engineers with high labor costs. If things go wrong, there is a large cost of non-quality, and all in all, the overall cost of laser cladding is relatively high. And that's why today you see it more used for repair operations, because there is you remanufacture capital goods, and there you can justify this cost. What we want to do now is, with LMD-AUTO, is go to a level of autonomous operation. So on one hand, it's automated pallet picking or bin picking. A robot picks up the parts, vision-based controlled, and that there is then robot-robot welding, so that there are no operators needed to feed the machines. But on the other hand, we also want to apply Industry 4.0 sensing and control to replace the operator-driven process control. And then the goal of LMD-AUTO is to increase the uptime, reduce the labor cost, improve the yield, and go to 24/7 autonomous operation. Good. Then, if you see the objectives, I think probably the most innovative objective for LMD-AUTO is to enable the turnkey operation by process control. And the crux is really that we have quite a lot of process know-how on laser cladding, let's say with the engineers and with the operators, and we want to combine, let's say we want to implement that knowledge inside the machines using Industry 4.0 technology. So it means that there are a number of sensor technologies, both used upstream and downstream, that are, let's say, welding procedures and methodologies to control and correct the clad. Experience that we apply today, work instructions, etc. And we want to implement that into the machine. So what we're doing there is we have a controller box, we have sensors, and at the moment it monitors. There are already alarm functions, and we want to migrate to active control. And let's say first step is that we, as I said, first apply the existing experience and working methodologies that we apply today in the operator-driven yeah, let's say, operation of the machine. We want to apply that into the software model. I think the next step is that we will make true use of, let's say, the large data quantities that we gather to achieve more insight into machine operation and the quality of the clad. Yeah. Good. And then what we think is that, yeah, let's say all the expertise should be inside the machine, and that will then enable a shift from white collar to blue collar. Yeah. Good. A second objective is more straightforward. It's really with the idea that you have one operator who can operate, let's say, 3 to 4 machines. Basically, he has to put, he has to make the materials available for the machine. But then we go to vision-based automated, yeah, let's say, picking of the parts of the pallets, and then he can continue fully autonomous with robot welding. Going to a cloud, so there is no machine downtime because an operator is working on one machine and one part is finished on the existing machine. So then there is more automation on that machine. Yeah. So it's another aspect, I think, of going to yeah, more automation towards machines. Then there are a number of other topics that we also could work on within this LMD-AUTO concept, but they're a bit outside the scope of this TRINITY project. Yeah. Good. Thank you. That's my part of the presentation. So yeah, if there are any questions, I will be happy to hear them.
Yes, thank you very much, Tom. We still have some minutes for questions and discussion. I guess the process control you are planning on this TRINITY, it's something that can be applied for other similar processes as well. But from the second objective on this pin picking and robot welding, have you had time to test it yet, or how do you see it's a simple task to complete, or what kind of challenges do you think there are in that approach?
Yeah, yeah, I think there is ideally have one system that has the flexibility to deal with a number of different parts and geometries. Yeah. The way we tested it already, let's say on lab scale, and there you see indeed part recognition and so on, it works very well. The other thing what you see is that, let's say, there is a difference between picking up a part and completely aligning a part so that you know this is the starting point for my clad, etc. Yeah, for the CAM program. And there we see there is still a challenge on how to completely do alignment after the part is picked up automatically, and knowing the exact start position for the CLAD program, where to start. Yeah. I think the other topic is perhaps not so much on the recognition, but more on strategies for, let's say, for example, picking up a part, putting it on a tool, yeah, and then start the CLAD, or picking up a part and aligning that part based on an extra visual check. So that we are investigating there.
Yes. So basically quite similar problems as in any pin picking application is to get the proper alignment.
Yeah.
We have one question from Pedro Tavares. Go ahead.
Yeah. Hi, Tom. Thank you for your presentation. I actually find it very interesting having two robots eliminating completely the shop floor logistics problem. However, I have a reservation when we consider welding in one of those robots, because you need to ensure some security and close the welding circuit. How do you tend to how do you how do we intend to do that? How do you manage to ensure security for the picking robot when the welding robot is working on top of a part that is holding by them?
Yeah, good question. So it's, let's say, one of the basic ideas that we have is that, yeah, I think you with, let's say, the automated process control, it kind of eliminates the need for an operator to enter the laser cladding cell. Yeah, and the laser cladding cell is a closed cell. Yeah, so that is, let's say, a first step in our HNS health and safety approach. And point is, it depends also a little bit, but typically a laser cladding process is a gravity-based process. So you don't spray the powder on the substrate, it just falls down in a coaxial nozzle, yeah, using the gravity. So let's say in most cases, in 90% of the cases, the motion of the laser cladding robot is really limited. Yeah, it's really the pick and place robot who picks up a part and moves that substrate under the laser cladding head. So it's really, let's say, it's one robot motion at a time, if that makes sense. And then, as I say, you have a closed system. The system stops if, for example, new pallet has to be entered to be made available with parts. And then if you close the door again, the cladding routine can continue.
Yep, I understand. Thanks, Tom.
Okay, thank you very much, Tom, for your presentation. I think we need to move ahead to stay in time. But if you have any further questions, you have the contacts of Tom there on the screen, so you can ask the questions also afterwards. But now we're moving forward, and this time we have a company from Netherlands, MX3D, where Thomas van Klaarbeke will be talking about warm clamp. Basically, it's an idea of combining standard industrial connections with wire arc-based additive manufacturing. And the target here is oil and gas industry and the maintenance needs there. Go ahead, Tom.
All right. Okay. Thank you for the introduction. My name is Thomas van Klaarbeke. I'm an R&D engineer for the 3D metal company MX3D. MX3D does large-scale additive manufacturing. And within the TRINITY project, we have two other partners to tackle the production of components for the oil and gas industry, more specifically clamps for pipelines. So what are these clamps for pipelines? Well, there are many different types of pipelines, sorry, that transport different types of fluids. This can be water, but this can go all the way to very corrosive or dangerous materials. These pipelines, of course, need maintenance, and sometimes a leak can be expected or a problem can be projected. And in that case, this pipeline needs to be fixed, basically bandaged, just like pipelines in your sink. If you have a hole, you need to patch it up. But of course, in the oil and gas industry, this is on a much more high level and secure way. So if a leak is expected, these type of clamps are being rapidly manufactured and put on the clamp. In an even worse case scenario, when there's already a leak, the pipeline is shut down, and this can cause losses of hundreds of thousands of euros to even millions of euros. As you can expect, an oil company, if it shuts down the production, it costs a lot of money. The production of these clamps, of course, needs to be done rapidly. Currently, this is done either with traditional manufacturing such as CNC milling. So these blocks we see here in front of us are milled back from slabs of metal, or they are manually welded from sheets of metal. And this brings me to the group we have established for this consortium. The first partner is Team, who is currently designing, manufacturing, and installing these pipeline clamps. The second party is MX3D, that's responsible for large-scale additive manufacturing of metal components. Third partner who does NDT inspections of metals and other materials. So first of all, Team, currently they are using CNC and CNC manufacturing. So they're manufacturing these clamps from metal slabs, or they're using manual welding. Of course, there are many different values that come into place when a clamp is produced, such as the design. This could be a material with very high standards that needs to have a lot of certifications, and then already a certain preferred design and material grade is picked. But it could also be that it needs to be installed very quickly, and that there are more manual welders available, so then they could opt for a different production process. So depending on the request, a different manufacturing method is chosen. Of course, these are always produced very rapidly, but there are always things to improve, such as material usage, or, for example, downtime, or more smarter planning of resources, in case, for example, certain machines are already booked, etc. The second party, MX3D, that's us. We are experts in additive manufacturing. What we do is basically create 3D metal shapes additively. So we're not subtracting from metal slabs, but we're building them up. And what we are using is wire arc additive manufacturing. And this means we are using a standard welding machine, and we are basically putting down weld on top of weld on top of weld to create geometry. So what you see here is a component for the heavy industry. It's a machine part, and this consists only out of welds. And WAM is known for being a very fast production process, because it has a production rate between 1 and 7 kilograms per hour. So this part in front of us is about 90 kilos, and it had a printing time of about 4 continuous days. So this is considered very fast for metal printing. The third party involved is TIAT. They're responsible for NDT, so non-destructive testing, and they do the inspecting and certification, so to say, of these materials. So depending, of course, on the requirements of the clamp, TIAT can give their approval on that it meets its requirements. So for the Trinity case, we are currently looking at the many different clamps that Team is producing and installing. These can range from very small pipes in diameter to very large ones. And of course, certain manufacturing methods are more beneficial than others for certain dimensions. And currently we are orienting ourselves where WAM and the existing production methods meet best for what shapes. To give you an impression about what WAM can do, here we have a pipeline connector, which is fully additively manufactured. And it had, I think, a printing time about 1 or 2 days. So this shows how the technique can be used to create spare parts or replacement parts very instantly. And because we're using welding wire and robots, this can be done on many different locations. So this is an added advantage as well. So if you're thinking about remote areas or areas on the sea, for example, you could have a very flexible manufacturing solution that can create many different parts. Instead of having, for example, a milling machine where you can only trim down metal blocks to a certain dimension, you can now build them up to however large you want them. And instead of having manual welders available, skilled laborers who are unfortunately it's a skill that is more and more harder to find. WAM can provide an automated replacement solution. So as I was saying, we're now looking at the many different types of clamps that are being used, and we're orienting ourselves together with our partners in the industry. And our goal is to provide an alternative manufacturing solution to the existing options. So to the existing CNC milling or manual welding, we want to do a hybrid approach where we use the advantages of each process. Well, mainly CNC. We're not thinking about manual welding anymore because we want to eliminate that. So we want to take the advantages of CNC milling, which is, of course, being able to very precisely fabricate metal objects. And the downside of CNC milling is the material wastage and, of course, the size of slabs you need. The advantage of WAM is that we can print whatever we need at a very high pace. But one of the disadvantages is that it's near net shape, it's welding. So it's relatively rough compared to CNC milling. So for the Trinity project, we're looking at what we can do for the oil and gas industry for the flexible and automated production of oil and gas components. And together with our third partner, TIAT, we are also looking at how we can certify the production of these components, because metal AM currently is in the beginning phase of certification. So this is definitely a first step towards it. And we believe that with our consortium that we can tackle, or we can provide the base steps in providing these manufacturing methods for the industry. As a final slide, maybe our one-pager. So our goals for the WAM clamp project is to reduce the lead time compared to other methods. Of course, we're not going to be able to reduce the lead time for any type of shape of pipeline clamp, but we have a few in mind that can benefit from it. We want to, of course, demonstrate our alternative manufacturing technique where we combine CNC milling or computer-operated processes together with wire arc. And of course, together with TIAT and the whole partnership, we want to accelerate the adoption of the WAM technology in the oil and gas industry, because it's in a very early phase. And we believe that by printing a demonstrator clamp and proving its quality features, that this will be a good step towards the right direction in adoption of metal AM. So this was my short presentation of our WAM clamp, and I'm looking forward to your questions. Thank you.
Thank you very much, Thomas, for the presentation. Yes.
It's a very good question. Residual stress is indeed a very big topic within the WAM world. There are ways to avoid it to a certain degree, is by designing in such a way that you avoid heat buildup in certain areas, or by doing intelligent path planning, so intelligent weld deposition. Sometimes it can be that it's not avoidable, the heat treatment, but depending on the use case and, of course, the amount of heat you put in, there are ways to eliminate the heat treatment process. So depending on the requirements of the clamp, or more in general of the object, the induced stresses might be low enough for it to go for installation. MX3D is an expert in toolpath planning, so this is something we are continuously working on. We are also monitoring the amount of heat we put in, and we are working with simulation softwares to avoid the stresses you are talking about. But sometimes there's no way around it, and parts do go into an oven to be heat treated. Our goal for the demonstrator project is to provide a manufacturing solution that is more efficient or faster than the existing options. We're going to look at whatever allows us to go there. If heat treatment is required. That's of course usually quite some hours of work to do. It's usually an overnight treatment or maybe a bit longer. But depending on the use case, again, this could still be a more advantageous solution over others.
Thank you very much, and we have a time for a very short question. This is X-Weld, presented by Pedro Tavares, the head of R&D at Sarkis Robotics in Portugal. And all the processes we have discussed today, they are welding processes, and so this X-Weld fits quite well into this group, and there's some interesting technologies that X-Weld is working on, and I think this kind of 3D sensors for part localization and robot calibration can be used in many different processes, not only welding. But let's let Pedro talk more about.
So first of all, thanks for your presentation of the project. So our objective is to tackle some of the difficulties that we typically found on shop floor for steel industries and other industries, but in this scope for welding in the steel industry. So I believe this is what I'm going to say now isn't new for most of you. Industrial robots are a mature technology. They are a catalyst for production. However, their full potential applications are still unexplored. And this is why we can see this in the currently collaborative robot phenomenon. We can also see this when we compare the number of industrial robots against the number of machining equipment, and this has a reason for it. During this project, we want to tackle the two main limitations on robotics and welding robotics. This is essentially the limitation related to the accuracy of industrial robots, and then the complex sensing procedures that are needed to automatically generate paths for the robot. It's typical to find operators, human operators on shop floor that need to program a set of parts, and this is typically a batch of small quantities, around 50 or less, and this takes about half a day to a full day, which will, as a consequence, lower the time of the operational time of the robot to around 50%. So what we want to do is, we believe that by adding sensing and advanced software, we will be able to reduce this time. We will be able to reduce obviously the return of investment of any kind of welding solution. And we also believe that this is a valuable solution because there is no other solution like this in the market at this moment. So in that regard, we are going to diversify our solution in 3 branches. The first one is the offline programming, where we are going to, by parts, identify the welding candidates. We are going to merge possible welding candidates and also take a 3D model of a part and detect where those candidates are, where do you need to segment those edges, which edges are good to be welded, and so on. Then we are going to generate collision-free movement vectors for the robot movement, for welding, for 3D perception, and so on. In this branch, we are also going to be able to see how the TCP is going to be in every part of the process, and we'll have a realistic process simulation of what is going to happen in the real work cell. And then, of course, we will have a final tab that is able to produce and to control the production of the robot and control the machine and the robot itself. And this will be accomplished using active perception and sensor fusion. We can consider this as as a result of integrating both local sensors and global sensors, and this will have a key part on the project as it will allow us to predict failures on the part and adjust the welding seam. And then we will have also a 3D sensing for robot absolute accuracy, where we can detect deviations. We can also detect deviations on the tool, and we can automatically calibrate that tool that will be the welding torch. So to have the local perspective of the sensing, we are exploring two segments of the market. One that is the 3D low-cost small sensor, such as the Intel RealSense or the Orbeck, and the other one that are typical industrial lasers. This can be laser lines or laser dots, but we believe that both approaches have some qualities. The first one, that will be the cameras, will allow us to have a wider perspective on the project and on the part, but they are typically scientifically proved, not industrial related. And the second one, the lasers are already validated in industrial facilities. So we start on them, but we intend to move on to the cameras. And then the global perspective, this is a setup scenario that we have on one of the partners of the project, this is NES. We have a global sensor that allows us to visualize the entirety of the work cell, and we draw every kind of interesting measurements on the part, on the robot, on the tool, and so on. This is how we intend to identify the object, identify the parts, the torch, what are the steps that we need to use on this sensing, and of course the output will be interactive work cell, virtual work cell that will be always updated, and based on that work cell we can compute the programming for the robot. So just to summarize the idea of the project, we are going to insert a 3D file, a CAD file, on our offline programming software. And this software will generate welding candidates, then generate the vectors for those welding candidates, and send a message to production control that will generate robotic programs. And then we will go and we'll input some information from the 3D global sensor vision, so that we can correct the robot and the part localization, the robot, let's say, the robot accuracy of the joints, and then we can also update the calibration of the torch, and then we will have a 3D local vision where we can detect with a higher precision some some faults that the part may have, and when correcting them, we can have a better perspective on the problem, and we can have and ensure a better welding. And so that's the presentation. I'm just going to put a video, and I will be able to answer some questions. So this video is essentially a preview of what we see for the project. It's obviously still in the early stages of the project, but yeah, I believe this should be a good example of what we want to achieve. And that's it. I'm ready for some questions if you have them.
Thank you very much, Pedro. Any questions on this topic? I think it's a quite interesting approach, and it can be applied in many different offline programming applications. Any questions to Pedro? So the focus of your demo applying is arc welding, which is quite programming intensive as such as a robot process, but have you plans on maybe also moving this to a different application? So are you purely focusing on the arc welding?
Yeah, our focus is obviously the steel industry. As artists, we believe this can be further developed to other markets, but our main goal at the moment is focus on steel industries, maybe some pipeline industries to do some sprinklers. But essentially, it's around industrial facilities with steel fabrication. So that's our goal.
Yes, and the plan is to create a system that includes both the scanner hardware and the software for the offline programming that utilizes these sensors.
Yeah, we believe one can't live without the other. We believe that the key for industrial success is to have a good sensing and then a good offline programmer, so that we can have the best of both worlds and ensure everything on the welding process. So the idea is to have a bundle that should include the vision sensing and also the offline programming of the robot. This can be generic, and we don't limit it to any kind of brand. This is a generic software, so we can just select the robot, select the components of the work cell, and autonomously adapt to the work cell and to the requirements. So that's the goal.
Okay, thank you very much. Any other questions to Pedro? Yes, so basically funding, do you have some expectations from Trinity where we could support you on this process?
Yeah, sure. First of all, I would like to thank our mentor, Igor. He has given us some good ideas on how can we proceed with the process and with the solution. And essentially, what we require is or what we need, we would like to have, is some feedback on the direction of the project, and having some kind of using your own software solutions and try to integrate them in our solution and see if everything we are doing now can be changed, or we can move our direction of our software in that sense. What we need is some kind of feedback and some directions on how to improve the communication with robots, the sensor vision framework, and that I believe you are sort of an expert, and we'll discuss further on the project.
Okay, thank you very much, Pedro. I hope we can help you on these challenges, and that's basically why we are here. So it's interesting projects as are the others. So I hope we also, as a consortium, learn a lot from these new technologies, and also how SMEs develop this and how they work, so that we can support you better in the future. So thank you for all the presenters today, and thank you for the participants. I think we had quite interesting presentations, and hopefully you learned something new. And you can be in contact with me or the presenters if you want to learn more. And please do check our web pages for how to get to our mailing lists and how to find some new webinars and new things we are doing. And basically here are the 3 remaining webinars that will be this week, Wednesday, and then again next week, Monday and Wednesday, same time and same procedure on all of those. And what we would like to hear from you is also some comments and feedback about this webinar. You can write it on the chat window if you have some improvements in mind, some topics you would like to hear about. Of course, these webinars are about the technologies that our third parties are working on the first demonstration program. But here are the contacts for the email, and please do follow us also on the social media on the new activities to come, and especially the coming second funding round that we will inform you in more detail later this year. But from my point of view, thank you very much once more for the presenters. Thank you very much for the participants. We had quite a nice crowd, and I'll hear from you and talk to you more on Wednesday. Thank you very much.